even though that's not a function, doesn't it still make sense for me to like say, hey, you know, go to this point and find me the equation of that tangent line? I mean, that still seems like I should be able to do that. Like, my calculus shouldn't like break down when you give me something that's not a function. I mean, there is a tangent line there. I should be able to find it, right? That would suck if our calculus didn't allow us to deal with this, right? Let me see. Let's get another. How about this one? X cubed cosine y. X cubed. Oh, thank you. Plus cosine y equals x plus y squared. X, is that right?
X squared plus y squared.
Oh, x squared plus y squared. No, it looks pretty close to the same thing. Okay, look at that right there in the blue. Is that a function of x? No. But even though it's not a function, I mean, I should be able to go somewhere and then find the slope of the tangent line, right? Here's the problem that we're going to run into, though. You know how before, if I was trying to find, like if I gave you a graph and I wanted to know the slope of the tangent line somewhere, all I would have to give you is the x value, and then you would go find me the slope? Like in the last problem we just did, right, that we did before we took a break, what was the x value that you needed to find that slope? It was 1, right? That's all you needed was the 1. Here, what's the problem if I just give you the x value? There's 2 y values that I could be talking about, right? I could be talking about this one up here or this one down here, right? If I give you this x value of 2, I could be talking about that point or that point, right? So giving you just x isn't enough. That's a problem. Let's look at the next one. Let me put that circle back up there. All of these have the same problem, right? Even on the circle, if I give you an x value, there's actually 2 y values that correspond, so there would be 2 different slopes. Okay, hold on. Cosine, what is it? Cosine xy equals 1 minus sine y? Oh, shit. Okay, now things are crazy, right? This is not a function of x. Like it fails vertical, horizontal, right? But I mean, come on, if our calculus is powerful, right, which it should be, I should be able to go to any point on here and find the slope of a tangent line. Like, right? Right? I mean, we don't want our calculus to be limited to just functions. Because in the real world, right, imagine you're trying to find, you know, when you think about like how calculus can be used, think about looking down at like a car traveling, right? The derivative gives you like the direction that the car is going at that moment. And then later on you can turn it into a velocity vector and physics stuff. But wouldn't it suck if we said, well, wait a minute, you can't drive like that. You're not allowed to. Like you have to drive so that it passes the vertical line test. That would be very limiting. So we need a way of dealing with this, right? How do we deal with things that are not functions? How do we find slopes of tangent lines? Well, this is going to require an entirely new method of taking derivatives. Not entirely new, but we're going to have to adapt our thinking on how we take derivatives, right? So I'm saying here is we can see that that the curves that I showed you are not true function of x. They failed the vertical line test. We have multiple outputs of y. That means if we're given an x, there's no way to tell which one we're talking about. So we now study a new form of differentiation called implicit differentiation. And you use it when you have implicit equations, equations you cannot solve for x or y. All right? And I'm going to just do a bunch of examples. So I think the best way to understand implicit differentiation is to just do examples. So let's start with this one right here. That circle, right? That circle that we graphed. I would like to know, can we find a formula for the slope of the tangent line? So I want us to find y prime. Now, I need to be more specific. I want to find dy dx. I'm going to switch to Leibniz notation. Leibniz notation is absolutely critical when it comes to implicit differentiation, because what this does is it tells you what your independent variable is. And that will make a little more sense as I do the problem, okay? I want to know what dy dx is. So here we go. Here's how implicit differentiation works. You start with the equation. You don't have to move anything around. You don't have to solve for anything. Just look at the equation. You're going to do an operation on both sides of the equation. You're going to do the same operation on both sides. You're going to differentiate. You're going to take the derivative. And you're going to take the derivative with respect to x, because that's what this variable down here is. So I'm now going to write d dx. I want to take the derivative on the left side of the equation with respect to x. And on the right side, I want to take the derivative with respect to x of the right side, 16. That's just, it's like instead of me using the primes, right, I'm using this d dx. And with implicit differentiation, this is absolutely necessary because, again, it keeps track of the independent variable. We're trying to figure out, like, if x is the thing that's being plugged in, how does that impact y? All right, I'm taking a derivative, and I have a sum. Well, good news. You can do the same rules we had before. Take the derivative of each one separately. So I'm going to make this d dx of x squared plus d dx of y squared, and then equals, let's do the right side right now. Isn't that a constant? And so the derivative of a constant is always 0 no matter what. Always, forever and ever. That never changes. Because remember, a constant is never changing. So the derivative is saying, how does something change? And if it's constant, it doesn't ever change, so that's always going to be 0. Y'all all right with that so far? Now we're going to take derivatives, and we are going to employ the chain rule the way that we've learned it, realizing that these are not as simple as they look. All right? How do we take the derivative of something squared? You bring the 2 down, right? 2 down, x to the first power, right? Times, now what? The derivative of what's in here, right? You understand what I'm doing? So I'm going to take the derivative with respect to x of what's in there. I know that that looks weird, but it was like, you know, I had an eraser squared. What's the derivative of an eraser squared? 2 times the eraser to the first power. Then take the derivative of x, but with respect to what? X. And what does dx turn into? 1. So that is just going to be 2x. All right? This is going to be just 2x. But look at this one. Okay? Look at this one. Same story. Eraser squared. What's the derivative of an eraser squared? 2 times eraser to the first power, right? That's a first power, not a prime. I'm going to take the first powers away because they look like primes. Am I done? No. Now I need to take the derivative of the y, right? But with respect to what? X. So I'm trying to take derivative of y with respect to x. This is not 1, is it? It's not 1. What is it? It's dy over dx. What's that? I don't know, but isn't that what I was asked to find? I mean, that is actually what I'm trying to solve for. It just appeared, didn't it? What I'm trying to find just appeared. This is dy dx. So I have plus 2y times dy dx. And then the right side of the equation is 0. Any questions? We're not done, but any questions on what I've done there? Start with the equation. Take the derivative on both sides with respect to x. Why with respect to x? Because I told you right here with respect to x. We do that here. Chain rule. 2 comes out. That to the first power. Derivative of x with respect to x is 1 plus, because it's a sum, plus just, we're going to do each one separately. Derivative with respect to x of this, power rule. 2 comes out, y to the first power. What's the derivative with respect to x of y? dy dx, which is what we're trying to solve for. What you're trying to solve for better show up, right? If it doesn't show up, how are you going to ever solve for it? So now let's get this by itself. So how do we get that by itself? Subtract the 2x and then divide the 2y. So subtract 2x on both sides, then divide both sides by 2y, and you get a final answer. Dy dx is negative x over y. We have a formula for the derivative. In other words, we have a formula for the slope of the tangent line, right? But this formula is different than any formula we've seen up to this point. Because what does that formula require in order for me to give you the slope of the tangent line? Both x and y coordinate, which is great because we had seen that on a circle, having just the x isn't enough, right? You have to have both. So this formula works the way that we would hope it would. I feel like I'm more excited than you are about this. This is exciting, no? No, it's not? Okay. 4. When this stops becoming exciting for me, this is when I stop teaching. This still blows me away that we've got a formula that's going to give us the slope of a tangent line at any point on that circle. So let's check a few points. Remember, the radius of this is 4, right? Can somebody give me the point up here? What's that point, x and y coordinate? 0, 4. Okay, now, 0, 4. What should the slope of the tangent line there be? This is by looking. 0. It should be 0, right? Let's see. Does our formula work? So at that point, 0, 4, dy dx would be negative, what's the x? 0 over y. And 0 over 4 is 0, so 0. So the slope of the tangent line is 0. Hey, that works, doesn't it? All right, what if we have done this point? 0, negative 4. Well, that just, we still get 0 on top, right? So it'd still be 0. All right, how about this point right here? What's the coordinates of that point? 4, 0. Okay, so if we go at 4, 0, what's dy dx? It's negative 4 over 0, but division by 0 is undefined. And hey, vertical line, right? Vertical lines, what's the slope of a vertical line? Undefined, right? So everything makes sense, right? How about this point right here? Now, you may not be able to tell me what that point is right off the top of your head, but what can you tell me about that point? Well, it's 45 degrees, yes, which means that these 2 points are equivalent, the same, right? They're the same because it's a 45-degree angle. So whatever this is, let's just call it, I don't know, P for point, and then that must be P as well, right? If we're at 45 degrees, right? If we're at 45 degrees, then those two must be the same. And if I plug that into my formula, right, what would happen if I replace x and y with p? What would I get? I get negative 1, right? Negative. Don't forget the negative there, right? So that'd be negative 1. Does it look like, are you pretty convinced that at a circle right there, that should be a slope of negative 1? See, everything works. I'm trying to convince you this formula works. Are you convinced? Yeah? All right. Let's look at the next one. I mean, there's good and bad news to that formula. The good news is we have a formula. The bad news is that we need both the x and the y. So you actually have to have the point to do it. All right, the other one we had here, where was it here? All right, let's do this one. X cubed plus cosine y equals x plus y squared. All right, that's practically impossible to solve for x or y. So I'm not even going to try. But I'm going to ask you to find dy dx again. So what am I treating as my independent variable? X. How do you know that? Because of the way I wrote this, right? So do you all see that this notation y prime is a little limiting, right? Because y prime doesn't tell you what your independent variable is. It just tells you, hey, I want you to take the derivative, which is fine until you get to this idea. Then you need a little bit more. I need to know what the independent variable is, right? So let's do it. Both sides. I'm going to take the derivative with respect to x on the left side. And then I'm going to do the derivative with respect to x on the right side. There we go. The good news is that I have sums between those, right? So I can do them individually. So I'm going to take the derivative with respect to x of x cubed plus the derivative with respect to x of cosine y equals the derivative with respect to x of x plus the derivative with respect to x of y squared. So I'm just doing each one separately, right? And we always what? Are we already what?
Oh, we already have a 1.
Yeah, we do have a 1. Everyone see that 1 right there? That's going to become a 1? I'll get to it, though. Let me start with the left. All right, what is the derivative with respect to x of x cubed? So we're going to use our chain rule. 3x squared, right, times now the derivative of the x with respect to x, which is 1. Do y'all want me to write d? I'll do it one more time. I'm just going to do it one more time. I'm taking the derivative with respect to x of x. That's our chain rule. Derivative of something cubed is this, times derivative of x with respect to x, that's going to turn into 1. All right, this one students struggle with. What's the derivative of cosine y? Negative sine y. I'm going to put it like that because I don't like the plus minus. So the derivative of cosine of something is negative sine of that something, right? Chain rule says then what? Times the derivative of what's in here, right? And what's the derivative of what's in there? That's d dx of y, right? That's the derivative with respect to x of y, which is really dy dx, which is what we're looking for, right? So there it is, right? The thing we're looking for just appeared. Everyone here needs to be comfortable with the idea that this is just the chain rule on this. Equals. Now that one is just dx over dx, that's 1. What's this one? 2y times, yeah, it's going to be dy dx again. I'm going to write it this way first, though. So that, again, we have that chain rule. The 2 comes out, 2y to the first power, and then d derivative with respect to x of y, which is the derivative of that base. Cleaning things up, we get 3x squared. That's just this. And we already said that that's a 1, right? That's 1. I'm going to go ahead and make this minus sine y times dy dx, which is the thing we're looking for. So that's this, equals 1 plus 2y times dy dx. So the thing that I'm trying to solve for appears in 2 different places, doesn't it?
Yes.
So if we're going to solve for it, we need to get it by itself. So the standard rule or protocol here is anything that has dy dx in it, move it to one side of the equation. Anything that does not have dy dx, move it to the other. So here's what I'm going to do. I'm going to kind of highlight this. That term has dy dx, and that term has dy dx. So I'm going to try and get those on one side of the equation. So I'm going to move this one to this side, which means I'm going to add it to both sides, right? And I'm going to move this 1 to that side, which means I'm going to subtract it. And that way I got everything that doesn't have dy dx on the left, everything that has dy dx will be on the right. And it doesn't matter which side you move them to, it's your choice. I moved this way because this one was positive and this one was negative, so when it comes over here, it'll become positive. So I have 3x squared, that's this. I brought the 1 over, now it's minus 1, equals, I had 2y dy dx, and then I brought that sign over and I had to add it to get it over here. You'll see that algebra there? Now, why do you think I did that? I can factor. I have a GCF on the right-hand side, don't I? They both have dy dx, right? So I'm going to pull the dy dx out of both of these. Just like you're factoring a number or some variable out. And you get 2y plus sine y. So if I pull the dy dx out of both of these out front, then I'm going to be left with the 2y plus sine y. We almost have dy dx by itself. All we need to do is divide. And if we divide through, we are there. 3x squared minus 1 over 2y minus, sine y equals dy dx. And now we have a formula for the slope of the tangent line, but you now have to provide me what? An x and a y. Give me any point on the curve, and I will provide you the tangent line at that point. Yes, slope of the tangent line. Yes?
What if you plug in a point that's not on the line?
Well, then you'll get a number, possibly, it depends, but it won't have any significance because it has nothing to do with the function or the graph, because that point doesn't exist on there, right? So you probably won't even know, you wouldn't even know that you have done something wrong other than the fact that, unless you get something like division by 0 or something. So you have to know the point first. All right, got the idea? Okay, I'm going to give you another problem here. This one's going to be a little easier. How are we doing? 15 minutes? 15? Something like that? Okay, this one's going to look a little nicer. X squared plus y squared equals 1. We already did a problem very similar to that. You know what? Let's make it equals y. How about that? Just to make it a little more interesting. All right, here's what I want. You ready? Find dx dy. What's my independent variable? Y, right? Not x. See, I switched it on you. That wasn't a mistake on my part. I did that intentionally. That means you're going to take the derivative on both sides with respect to y, not x. So now it looks like this. Derivative with respect to y on the left equals derivative with respect to y on the right. Now you might be asking yourself, like, well, what the hell is dx dy? What does it represent? Remember dy dx was rise over run? All dx dy is run over rise. So it's just flipping the ratio over, which in some instances we want that other than the other way around. Just depends on the context of the problem you're working on. Reciprocal. It depends on how you want to use the word inverse. Usually inverse is more of like a functional thing. So I would say reciprocal more than inverse. All right, how do things change? All right, when we do our first derivative, we're going to do derivative with respect to y of x squared, and then plus derivative with respect to y of y squared, and then equals the derivative. Hey, isn't this just dy dy? So dy dy becomes the 1 now. Do you see how things are kind of switching places? So this becomes 1 on the right. What does this become? 2x times dx over dy. See, you're looking at this chain rule, right? You've got this black box squared. What's the derivative of the black box squared? 2 times the black box to the first power. Now you have to take derivative of that x with respect to what? Y, and that's no longer a 1. It's dx dy. But are we happy to see it?
Yes.
Absolutely, because that's what we're solving for. You see? Plus, now this one, same idea. We have a box, right, being raised to the second power. We get what? 2y. But then what? dy dy, right? Because you got to take derivative of that y with respect to y. So you get dy dy. And that is going to become a 1. And so here's where we are. We've got 2x dx dy plus 2y equals 1. Pardon me? Yeah, the dy dy now turns into a 1, just like this one turns into 1. See, before dx turned into 1, right? Now only dy dy turns into 1. And the dx dy just stays there. And now I can solve for this, can't I? Move that to the other side, and then divide by 2x. dx dy equals negative 2y, and then divide dx dy equals, what is it? Negative y over x, right? Because the 2's cancel. Oh, plus, oh, I'm not, yeah, sorry. That's my mistake. I was doing the other problem. 1 minus 2y, and then divide that by 2x. Okay, there we go. I have time to squeeze one more in here. Same problem. X squared plus y squared equals y. Same exact problem. All right? Here's what I want you to find. dy dt. What? That should be making you kind of go, what? Like, what are you talking about? I'm not sure I understand. Why is that a little different than what we've had before? You don't have any t's in that problem, do you? Nope. Got to leave the x and y's alone. So let's just follow the procedure we've been doing. What is our independent variable? T. So we're differentiating with respect to t, right? So that's what I'm going to do. I'm going to take derivative with respect to t of the left side, and then the derivative with respect to t of the right side, which is just y. Let's start with the right side, because there's not a lot to do there. Do you all agree that dy dt is not 1? Right? This is not a 1. In fact, are we ever going to get 1s? No. Why? I don't have any t's, right? So I'm never going to get a dt, right? Never going to happen. But I can tell you that the right side is dy dt, and I'm happy to see that. Yeah, because that's what I'm looking for, right? So at least what I'm looking for is here. Now over here, let's split this up. Derivative with respect to t of x squared, then plus the derivative with respect to t of y squared. Chain rule on both of those. All right, what is the derivative of x squared using your chain rule? 2x first, right? 2x, but then what? Times what? dx, you have to go and take the derivative of this base, right? dx dt. What the hell's dx dt? I don't know. Whatever dx dt is, that's what, I mean, there, it's there. And then I do plus, and now what's the derivative of y squared? 2y times, chain rule, dy over dt. And at least for that, that's what I'm trying to find, right? That's what I'm trying to solve for? It appears twice, doesn't it? Okay, so I'm going to move this to this side. Let me get all my dy dt's to one side. 2x dx dt equals dy dt minus 2y dy dt. Why did I do that? So I can factor the dy dt out. Good. I'll be left with 1 minus 2y when I pull a dy dt out of both of those. And then just divide through by 1 minus 2y, and I'm done. Now, what I just did is just purely mechanical. Right now, we don't have a whole lot of meaning as to like what the hell this is. But I will point out, in order to know what dy dt is, what do I need to know? I need to know x, right? I need to know y, and one more thing, dx dt. What the heck is that? Well, stay tuned. We're gonna see how this relates to word problems. We're gonna need this method. So the moral of the story here, I guess, is that you got to be real careful about this, right? So I like to, you can start